Hi, we're talking about dot products today, and in talking about dot products we're going to go back to our familiar work application. Work is force times distance, and it's the force in that same direction. Well, let's just say that the force happened to be at an angle. Work, which would be a dot product, which is how we're going to describe it here in just a second, would be the magnitude of both the force and the distance, but it would be that fractional part, or multiplied by the angle, the cosine of that angle in between, because it wouldn't be solely in that one direction. So it would just be a partial of that. Now the dot product is going to be, we're going to define it, and this is our definition. No explanation needed. It is a definition. It's the magnitude of vectors u and v times the angle of the cosine times the angle, the cosine of that angle in between. Alright, that's what I'm trying to say. So if I have two vectors, and let's just say that the vectors are in the same direction, so the vectors are in the same direction, both u and v are in the same direction, then it would just be the cosine of that 0, which would be 1. So it would just be the two magnitudes multiplied together, which is the same as this work example up here at the top. Let's look at another special case, and that is if, let's just say, the force and the distance are basically, the distance is in the, let's just say that this is distance and this is force, and let's say that they are in opposite directions, in that the distance is left and right and the force is up and down, and I want to know the work due to that force. Well, there's no distance moved in that y direction, so the work there would be 0. So the next thing that we'll talk about is a special case, and if the vectors are parallel, note that it's the same as just saying that it's the cosine of that 0 degrees, because they're in the same direction. So just be those two magnitudes multiplied together. However, if they are perpendicular to each other, meaning that we're wanting to know what the work is done, and the force happens to be vertical and the distance happens to be in the horizontal, there's no work done in that vertical direction. So those dot products are going to be equal to 0, and we're going to define that as orthogonal vectors, meaning that they're totally perpendicular to each other. So let's look at a couple of cases here where I've got some vectors and I want to know the dot product. Alright, I went ahead and got the magnitude of u and v, and then I'm going to compute the dot product, and since the cosine of 90 is 0, then the dot product of vectors u and v is 0, which means that u and v are orthogonal, or perpendicular to each other. And we can note that we've gotten the magnitude of u and the magnitude of v. That means that this length of this line is a 2, the length of this line is a 1. We can compute the angle in between by saying that this is a right triangle, and the cosine of theta is adjacent over hypotenuse, so that would be 1/2. They went ahead and found theta, but there's really no need. I can say that the dot product of these is, going back to my definition, cosine theta, plugging these in, I'll get 2 times 1 times 1/2. The dot product between these two vectors is 1. Theorem 12.1 can be proven using the law of cosines, and what it tells us is that we've got a really cool way of finding dot product if it's written in this particular vector form. So that's very nice. Let's go back to our other one. I can just add up. I'll say the u in the same direction, it would be the u1 times the v1 added to the u2 times the v2. So I'm going to go back to my other problem and see if that would have worked. Could I have just taken the uv and just say that it is the square root of 3 times 0 added to that 1 times 1. Oh yeah, I did get the same thing there. Let's check in this other case. In this other case, I have, let me just go ahead and write down plus 0i plus 0j, and then this one would be plus 0k, and notice that because I don't have anything in the same direction, their dot product would be 0. Alright, I want the dot product between u and v, so I'm going to get that, and what I do is I take and multiply those two in the same direction. That would be square root of 3 times 1, add to it the next direction, the j direction, that's 1 times square root of 3 plus 0 times 0. Well, that's out of there. As soon as I write down the first 0, I'm done there. And this would just be 2 square roots of 3. For the next one, I'm going to find the angle between u and v. Well, I have just calculated the dot product using that theorem, so that's going to be pretty handy. And let me write down my general definition for dot product, because I'm going to be using that. And cosine theta. So I'll know that this guy is 2 square roots of 3. The magnitude of u is going to be the square root of square root of 3 squared plus 1 squared. I'm not writing down the 0 times the square root of, and that would be 1 squared times square root of 3 squared, not writing down the 0, times the cosine of theta. And I'll do that algebra for you. Alright, so cosine theta is going to be square root of 3 over 2. Well, that's pretty convenient. Since theta is in between 0 and pi, I know that theta is pi over 6. Alright, C is going to be done similarly. Alright, so I just wrote down the definition. I went ahead and said the two components in the I direction for u and w multiplied together, added with the two components in the j direction, add that to the multiplication of the two components in the j direction. And that's going to end up with, once again, 2 square root of 3. The next is 2 times, and this ends up being square root of 16, which would be a 4. Cosine theta, and then I'll get that cosine theta is 2 square root of 3 over 8, and then cosine theta is square root of 3 over 4. You'll have to do an inverse cosine and get an approximate answer, and you get about 64.3 degrees. And that's the angle between those vectors. Just another note about looking at the properties of the dot product. It would make sense due to the fact that multiplication is commutative here with the definition of the dot product, that the dot product itself would follow the commutative property. Then the associative property, it's all multiplication and it's commutative, so that would make sense that it would follow the associative property, and the distributive property as well. And those properties can be proven just using the definition and this theorem 12.1. Your textbook has a nice animation in discussing these orthogonal projections. What I'm looking for when I am looking for the projection, orthogonal projection of u onto v, is I'm basically looking at the shadow that u creates on v. And as these angles change, the shadow becomes either greater or less at this orthogonal position, or 90 degrees, there is no shadow. And then as theta becomes larger than pi over 2, then we have a shadow that is in the opposite direction of v. So when we're looking for the orthogonal projection of u onto v, we're looking for this vector in itself that's either in the direction of v or in the opposite direction of v, and also finding what's called that scalar magnitude of u onto v. So here we have a nice little flashlight, and we can see the flashlight shining down from u onto v, and that would be the orthogonal projection of u onto v, and it would be that vector along that direction of u, unless this theta happens to be greater than pi over 2, in which case we have a projection that is in the opposite direction. Now, these are our definitions and how we get those values. So let's play with them. First off, they want me to find the projection of u onto v. That's how I would state that, the projection of u onto v, and the scalar component of u in the direction of v. Just wanting to know that magnitude. And we're supposed to find that for both. Now, in my first problem, it would be nice if I could just use this straightforward formula right here, but I can't because I don't know the cosine of theta. Of course, I could go and find it, but I have another way of finding it. If I want to find, let's do the scalar one first. If I wanted to find the scalar, I just take the dot product of u and v, divide it by the magnitude of v. Alright, just using the theorem that we learned, I am going to multiply 4 times 3. Those two vectors are in that same direction, or those two components. Add to that 1 times 4, the two vectors, the two components that are in the j direction. And then I'm going to divide it by the magnitude of my vector v, so that would be 3 squared plus 4 squared, and I'm going to compute that for you. Alright, so I got 16 over 5 for the scalar component of u in the direction of v. Next, I need to find the projection of u onto v, and I could choose either one of these two that I wanted to. I happen to like the first one because I already know these quantities, so I'm just going to use that. I know that the scalar of component of u in the direction of v is 16 over 5, and then I'm going to multiply that by just the straight vector v, which is 3, 4, and each of those values needs to be divided by my magnitude of v, which is 5. I found that before, so I'm going to be writing that down as 16 over 25, 3, 4. So that projection of u onto v is a vector in itself, and it is in vector form. And then I'm just going to play another one, so I'll write that down. Okay, what I have so far, I just plugged all of this in. Notice that the scalar component of u in the direction of v is negative. That just means that that angle between them was greater than that pi over 2. Finishing this projection of u onto v, that's going to be negative 1 over 2, and he has that vector components 1, negative 1, with the magnitude out front of the negative 1 over 2. We began our lecture in this section talking about work, and how work was just the dot product of force and displacement, so I need the displacement. If they're asking me to find the work, I'm going to need to find that displacement here between these two vectors. So D in this case would then be just my, if you'll remember from a section or two back, in order to get that displacement you're just going to take the Q minus the P. So that's going to be 6 minus 1, that's 5. 6 minus 1 again, that's 5, and then a 0. So there is my displacement. If work equals the dot product of force and displacement, then what I'm going to do is just compute by taking those values in those components in the same direction, multiplying them 3 times 5, added 2, 3 times 5, added 2, 2 times 2. This is going to be 30, and I believe the unit on this is joules. That makes that pretty simple if I know what that vector is in that ijk direction. A very common problem has to do with finding the normal component of a force if you have a block or something sliding down a plane. In order to do this, what we're going to need is we're going to get the unit vector. And the unit vector, we have it drawn for you right here. It just shows that we are sliding down, so we're going from our standard position down with at an angle of -30. So this unit vector, how they got this value was they just said that V is, and they said the cosine of -30 in the degrees in that x direction, and in the y direction it was the sine of -30 degrees. And then they got this square root of 3 over 2, and then the -1/2 in the I and j directions. So for the F, there's my unit vector, there's my F vector. He is acting exclusively in the downward direction, so his vector is just a 0 in the x and a -10 in the y. Next, I need to find the projection of F onto V. So the projection of that force onto V. So I want the projection of F onto V. And I'm going to use the formula given where I find the dot product between F and V, and then the dot product on V itself, and this answer will then be a vector. So the dot product of F and V, how I do that is I'll multiply those values in the same direction. So it's going to be 0 times the square root of 3 over 2. So 0 times square root of 3 over 2, so I'm just going to write a plus 0 there. And then it's going to be the -1/2 times the 10, so that's going to be a 5, over, and then the dot product of V on itself is then going to be the square root of 3 times the square root of 3 over 2 times the square root of 3 over 2, which is 3 over 4, plus I want the -1/2 times the -1/2, which would be 1/4, times that vector V, and that vector V, which is our unit vector, is the square root of 3 over 2, -1/2. So when I project that force onto V, I get, this is going to be a 5, square root of 3 over 2, -1/2. Now for that normal component, all I need to do for that normal component is just take that vector f and subtract off the projection of f onto v. So that would be f was just, there he is, 0, -10, minus 5 times the square root of 3 over 2, and then the -1/2. And just doing that arithmetic, you will get -5 square roots of 3 over 2. And for the j direction, you'll get -15 over 2. And that's how you'll get the normal.